Bismillahirrahmanirrahim. The last lecture of this week is on a typical example to find out the MIMO capacity uh, of a system in which we have performed SVD decomposition of the MIMO channel. So this is lecture number 26 of week 11 for the course of Advanced Wireless Communication at IST. So let's take a SVD MIMO transmission and capacity example of a 3x3 MIMO system. Let's see if we can decompose this channel through SVD and then find the maximum sum rate capacity that it can achieve. So normally SVD is applied on a matrix which has more number of rows and the columns in which R is greater than T. But here we take an example of a MIMO channel matrix H, which is a square matrix in which the number of transmit antennas is equal to the number of receive antennas. So we have a channel matrix which has these elements. The interesting thing about this channel matrix is that the columns of this channel matrix are orthogonal to each other as depicted here. So that's an example of first two columns, which gives the result if you multiply in such way equal to 0. Now first let's try to decompose this channel into SVD. So the first thing is you can do is you can normalize each column of H as follows by dividing the each element of the columns with the normalized version of that column. The normalized version of C1 is under root 13, under root 52 for the second column, and 2 for the third column. So what we have here is what we could do is decompose this search matrix into this normalized channel in which you have this matrix to be equal to U, and you have the remaining thing that you get is the the diagonal matrix. So the point here is when you see this diagonal matrix, it does not satisfy the property that the uh, eigenvalues are ordered. So here the first eigenvalue is smaller than the second eigenvalue, which is larger than the third eigenvalue. So these single values are not in decreasing order, they should be in decreasing order. So what you do is you flip the first two columns. If you flip the first two columns of this two matrix, then you flip the two columns of this the rows or the columns of the second matrix also. So what you get here is, now when you flip this matrix is still a U matrix which has orthonormal property, and this matrix can be basically again converted into these two matrices. By multiplying this matrix by this matrix, you will get this matrix. So first we have got this matrix by flipping, and then we have again split this matrix into these two matrices. Now you see that the E matrix, which is the diagonal matrix, contains the eigenvalues which are decreasing in order, and then you have a V matrix here. So if you see closely, that this is the orthonormal matrix which has U Hermitian multiplied by U is equal to identity matrix, and similarly this is a unitary matrix which has the property of V Hermitian, V is equal to V into V Hermitian, that is equal to identity matrix. So if we see the singular value matrix or the diagonal matrix, we have sigma 1 is equal to this, sigma 2 is equal to this, and sigma 3 is equal to this, and these eigenvalues are ordered and they are in decreasing order, and they are all greater than equal to 0. So what we saw that at the receiver side, what we have is we multiply the received signal vector with UH. So this is UH, we get this thing. At the transmitter side, we do pre-coding, we multiply the symbols, whatever those symbols are, with the V matrix. This is called transmit pre-processing or pre-coding. So the actual received signals that we get would be then equal to this diagonal matrix multiplied by the transmitted signals. So we have three decoupled channels now. If we multiply and get each values of y1, y2 and y3, we get these things. So actually the channels were mixed and the symbols were mixed as follows. If we take the simple linear equations, so we see that y1 is equal to 2x1 minus 6x2 plus 0x3 plus w1. So these are not parallel channels because all the symbols are somehow multiplexed at each received antenna y1. So Now this thing has been converted into spatial multiplexing, into parallel 3 decoupled channels. All the symbols are decoupled. Y1 only contains information about x1, y2 about x2, and y3 about x3. So it is very easier at the receiver side to extract x1, x2, x3 by just inversion. So now we see the capacity. How to find the optimum power allocation? It is the same thing to find out the capacity or maximize the sum rate or the Shannon rate. So as discussed in the last lecture, the P1 can be found out by finding the value of this function, and similarly P2 can be found out finding the value of this function, and P3 can be found out the value of this function. Now assume that the noise power at each channel is independent and is equal to 0 dB. So sigma square is equal to 1. So assume that the total transmit power is equal to 3 dB. It means power is equal to 2. 3 dB means twice the power. So the total constraint is sum of all the powers in each channels, that is equal to 2. Now we have to find out which channel should get what power to maximize the sum rate or to maximize the total sum of the capacities of individual channels. So what we do is put the values of P1, P2 and P3 calculated here. So from here you can find a scalar multiple, which is the Lagrange multiplier. That Lagrange multiplier would be given by 1 over delta is equal to 0.7821. So P1, P2 and P3 are the powers for optimal power allocation. So if we put the value of Lagrange multiplier in each of these case, you will get power 1 is equal to minus 1.1755 dB, similarly minus 1.517 dB, and P3 would be minus 2.74 dB. So if we allocate these powers to the each channels, then allocate powers to these channels, then the overall maximum sum rate would be maximized. So if you see closely, the power allocated decreases as the gain sigma I square of the channels decreases. So that is why it is called water filling power allocation.